So, we had this as our equation. So your enthalpy of your reaction is your standard formation of your products minus your enthalpy of formation for your reactants. And the reason why you have this negative sign is why?
Oh, because it's exothermic. Because, oh.
I just said it like that.
Well, I mean, it is exothermic because you're doing the opposite.
Yeah, am I forming reactants?
No, now you're breaking.
I'm doing the opposite of forming.
That's what we're back to.
Any equation is break down reactants.
If you're breaking it, it's releasing it, right?
No.
Well, it takes energy to break bonds. It's actually the releasing of energy comes in the forming of bonds. Because typically, like for example, if I've got reactants, they break down to form just like elements / atoms. Right? That's what's left when you break down a compound. And then they form products. Okay? This is more stable than this. Always. Well, almost always. Where compounds bond. Why do compounds bond? Why do things bond? To be what?
Stable.
Stable. So breaking a compound down is going to make it less stable. Well, less stable means high or low energy. High. So I would have to have put in energy to break the bonds.
Activation energy.
Well, then this has high energy. Or higher, maybe I should say that, than this does. But this usually has lower energy than the elements, because when they bond, they do it to be more stable. So what you have is, it always requires, every chemical reaction requires energy to break bonds. Every chemical reaction gives off energy when bonds are formed. Every single time. Now, the net is dependent upon, did it give off more in forming, or did it require more in breaking? Does that make sense? If it requires more to break the bonds than energy given off when they form bonds, it's going to be endothermic. Because more energy going in, less energy going out. But, if it didn't take that much energy to break the bonds, and we formed really low energy products, a lot of energy got released, then we have an exothermic reaction. Does that make sense? Yeah.
So for change the H of the reactants, you would just do all the reactants, just plug those numbers in for the table?
Yeah.
Okay. And just add them together, or not add them, right?
What was that?
You would add them together, not multiply them?
Yeah, you add them together, you multiply by the coefficient, which we'll get to here in a second. It's not hard. Okay? So, go get to the back here, what is that, A21, A20? So we want to find the enthalpy of reaction, and we can use Hess's law and the formation enthalpy values to figure this out. So here's how this works. If you look at in your appendix, what is the units for your formation numbers there? H of F. Kilojoules per mole. Well, we have more than 1 mole on these guys. So we have to take that into consideration. So if I do products minus reactants, let's start with my first product. Okay, I have 4 moles of it. And I know that NO2 as a gas has to form it would be how much energy per mole? What does it say? 34 kilojoules per 1 mole. Okay? That's the amount of energy that would be required or would be released when this gets formed. Well, actually, it's positive? That was actually a positive number?
Yeah.
Oh, this is one of the guys that's actually more stable not in this form. That's weird.
Yeah, it is.
There's not many of them, is there? Most of those numbers are negative, aren't they?
Yeah.
Yeah.
Or 0.
Or 0. Which means it's actually more stable for nitrogen and oxygen to be in their N2 and O2 form than it is to be in this form. Interesting. Okay? Plus, I'm going to add the energy from this with the energy from this released in that situation. 6 moles. It should be like negative 280 something. 286. Now notice water, when you form water, a lot of energy is given off.
Yeah.
It's way more stable than just having hydrogen gas and oxygen gas.
Yeah, because it forms a. Can you tell that by the fact it forms liquid, not another gas?
That's part of it,
Would that
probably.
be a result of that?
Yeah, part of it. You also got to think about the.
Yeah.
There's a lot of factors that I've found as you progress here. It's never based on one thing. Okay? Then we're going to subtract. It's really important that we're distributing the negative to both of these reactants. Make sense? So we got 4 moles. It's also important that you make sure that you note the state, because some of them have different numbers based on their states. Negative what?
Negative 46.
It's a gas, right?
Yeah.
Yeah, negative 80.
Negative 80?
No, what? What's NH3?
Yeah, the gas.
That's aqueous.
Oh, yeah, negative 46. I was like, no, guys, it's.
No, I was like, no,
negative
you're
80.
46, you said?
Yeah.
Okay, and we know this is in
0.
its standard form, so I could just plus
0.
7 times 0.
0. That's nothing.
I know, but I want to show you. So if I were looking at this, I could look at this and say that this guy is going to be a very favorable reaction from a heat energy standpoint, because I'm looking at forming a really negative thing here, and it only requires a small breakdown of bonds. So my guess is you're going to get a fairly exothermic thing here. Not like extremely exothermic, but decent amount. What'd you guys get?
Negative 1,396.
So that's not that.
What was that?
That's not that.
Yeah.
That's pretty
We're just
excellent.
finding
Yeah.
out right now, point back in. But.
Okay, now I want to show you something. This is just the energy given off for this whole reaction. Let's quickly review what that very first day that I said was going to get easily forgotten. Let's say that I had like 30.5 grams of NH3 in this reaction. How much energy would be given off in this reaction if I only had this and I had excess amount of this? So this is, I'm saying this is the limiting reactant. Does that make sense? You would take this, you would convert it to what?
Moles, and then plug it into what we just did.
No, don't you do the negative 1,396 over 4?
What is this? It would be 14, 15, 16, 17.04.
Yeah.
What that does is converts this to moles. And I know that this much energy is going to be given off per how many moles? 4.
Oh.
I don't have 4 moles of this. If I had 4 moles of this, this is how much it would give off. I don't have 4 moles of that, so it's going to give off less. Does that make sense? So this would be the energy had I had the correct moles of everything. Well, if I don't have that much, it's going to give me less. If I have more, it's going to give me more energy given off. Does that make sense?
Negative 620.
I don't have a number, I just made this up, but like I just wanted to show you the process again. Okay?
Negative 624, right there. No, I forgot about that.
I want you guys to do this one really quick.
Ooh, thermite, that's what blows up, you know what I mean?
Oh no!
Thermite's a lot of explosives. Yeah. Because it explodes.
Really exothermic.
Yeah. That's it. No. O2 gas, 0. Oh. Diatomic gas, 0. 1 oxygen is 249. One, it's not that.
No, it doesn't.
Any diatomic thing is.
I see it.
You guys do this one.
I'm trying to.
Do the one that I just had you do. I'm going to put up some information for this next problem so that we have time to go over it.
The aluminum oxide.
Is that not in there?
It's on the first page. Just take the turn page and start the other page.
Oh, right there, thank you.
Can you answer that? Still working?
Fe2O3 is what that is. Fe2O3.
What'd you guys get?
Negative 850.
Yep. Griffin?
Yep.
Okay. We've got 7 minutes here to go through this problem. What they're saying here says, until recently, methanol was used as a fuel in high-performance engines in race cars. Using the data from table 6.2, which I think there's some enthalpy values in a small table in 6.2. There's big tables in the back, right? Compare the standard enthalpies of combustions per gram of methanol with per gram of gasoline. So this here is methanol. Here's your gasoline. All right? What I want you to do is figure out the enthalpy of reaction for both of them, and then we'll figure out per gram. I gave you all the numbers so you don't have to look in your book. Okay, can you do that for me? Actually, why don't we have Ryland and Benjamin do this one, Nathaniel and Annie do this one. What?
You just call me Ryland, the event. It's not the event of my name.
We're gonna say Ryland. Ryland and maybe
Okay,
I
never
said
mind.
that like
Maybe
too close together. I don't know.
it's not a huge deal. It's just funny. People call me Ryland more than call me Ryland.
Is that -786 for 2 weeks?
That number on the far left is 239. Far left.
239 negative.
Those numbers minus that number. It's products minus reactants.
Yeah.
Yeah.
What else is here?
Products, no, it's not.
Oh, yeah.
And 2. And 0 in there.
Got answers for these?
I haven't.
So which one are you doing?
The one that left on is
Okay, what'd you get?
14.4 or negative 14.4.
Approximately that.
Yeah.
Is it you, Griffin? Do you second that?
I didn't actually know. I think I did something.
Annie, what did you get for the next one? 10,096, you mean?
That's what I got.
You got 10,900?
Okay, 10,906.
I got negative. Or it should be negative. Otherwise, it doesn't make sense to the problem. That's true, that's a good point. Otherwise, it's a fuel that's absorbing energy, and that's not.
Yes, you're right,
that's not-
10,900, yeah.
That's not useful. I want a fuel that fuel up a car battery.
Okay, so, whoops.
It's completely useless in a car.
Okay, those are your two numbers there then.
Good for like, cooling.
Okay, those are your two numbers. Now that would be the energy for the reaction. So if I want to know how much kilojoules is given off per mole of each of these things, I would take this divided by 2 to get per mole of that, this divided by 3 to get per mole of that, this divided by 2 to get per mole of that, this divided by 4 to get per mole of that. That make sense? Same thing I could do with this with all of the coefficients over here. Well, they wanted to specifically know methanol compared to gasoline. So I want to know per mole so I can get per gram. Divided by what? Then I'm going to take that and get it per gram by plugging in what? How am I going to get this to per gram after I've got per mole? Molar mass. And I'll give you the molar mass for time purposes. Okay, that should give you sit on my on this side.
I know.
How do we have negative grams?
It's energy per gram.
Oh, okay. Got it.
Interesting that they chose to use methanol in their high performance engines.
When gasoline works better.
Gives you more bang for your buck. So I'm guessing if they were using methanol, they were filling up with gas way more often. Right? You get about twice as much, bang for your buck when you fill it with gasoline. You can go probably twice as far using gasoline than you can using methanol. Now, I don't know why they chose to use methanol, if it was just cleaner.
Or it's cheaper.
Well, it probably was cheaper too.
What made it better for a car?
Now, it does say gasoline is actually a mixture of compounds. It's not pure octane. So it probably isn't quite that good, if that makes sense.
Why wouldn't it burn for your octane then?
Because it's very difficult to purify octane.
Oh.
As you guys read, I think in one of the next couple lessons, when you frack oil, it gives you a range of hydrocarbons, not a pure octane. Okay, questions?